day everyone, in this video I will be discussing about superposition of waves in qualitative and quantitative description. So what is superposition of waves? Superposition of waves leads to phenomena such as interference and beats. The principle of superposition states that when two or more waves overlap, the supporting disturbance is the algebraic sum of the individual substances. In Figure 1, it shows two waves with the same amplitude approaching towards each other becomes and superimposed as they meet. Eventually, the waves overlap, producing a wave that has twice the amplitude, and then continued unaffected by the encounter. The pulses are said to interfere, and this phenomenon is known as interference. This means that when two waves combine, it forms a new wave pattern. As shown in the figure, two waves with the same amplitude moves toward each other and overlap, creating a single wave with a larger amplitude. And after overlapping, they continue moving and change. In qualitative description, waves pass through each other without being destroyed. At overlap, displacement adds up. Then, wave interference is the phenomenon that occurs when two waves meet while traveling along the same medium. So there are two types of interference. The first one is constructive interference and destructive interference. Constructive interference occurs at any location along the medium where the two interfering waves have a displacement in the same direction, while destructive interference is interfering waves have displacement in the opposite directions. The figure shows the two main types of wave interference, constructive and destructive interference. In constructive interference, the two waves meet and their crests and troughs line up in the same direction. When this happens, their energies combine, producing a larger wave with greater amplitude. This can be seen in the top part of the figure, where the two waves overlap to form a taller wave. A real-life example of this is when two ocean waves crest to crest, creating a much bigger wave. On the other hand, destructive interference occurs when one wave's crest meets another wave's trough. Since they move in opposite directions, they cancel each other out, resulting in a smaller wave or even a flat line, as shown in the bottom part of the figure. This can also be seen in the ocean when the crests and the troughs from different waves meet, making the water surface appear calmer. In short, constructive interference strengthens the wave, while destructive interference weakens or cancels it. What is standing waves? Standing waves occurs when two waves of the same frequency and amplitude are moving in opposite directions and interfere with each other. When we say nudes, it has no displacement and amplitude is always zero, while antinudes is when amplitude fluctuates with max intensity. In the diagram, the nudes are shown at points where the wave crosses the center line, while the antinudes are the peaks and troughs between them. A common real-life example of a standing wave can be seen in a guitar string. When you pluck the string, waves travel back and forth, reflecting from both ends and forming nudes and antinudes along the string, producing musical notes. In quantitative description, superposition of waves is when two or more waves overlap in space. The resultant displacement at any point is the algebraic sum of the displacement produced by each wave at that point. So the formula to be used is y1 equals a1 sine times angular frequency times time plus key x1, and y2 equals a2 sine multiplied by angular frequency times time plus key x2. And due to superposition, the formula will be y net equals y1 plus y2. Let's solve this example. Two waves traveling through the same point are represented by this. Find the displacement of the particle at x equals 6 cm and time equals 3 minutes. First, the given time is 3 minutes, and it is converted into seconds because the standard unit for time in wave equation is seconds. So, 3 minutes divided by 1000 equals 0.003 seconds. Next, the wave equations are used to find each wave's displacement. For wave 1, the equation includes its amplitude, angular frequency, and phase angle. The computation shows how the sine function is applied. y1 equals 1.5 cm times sine 2.4 pi, which gives approximately 1.43 cm as the displacement of wave 1. For wave 2, the same process is done using its given frequency and amplitude. y2 equals 1 cm sine 1.2 pi, which result in approximately negative 0.588 cm as the displacement of wave 2. From the previous calculations, wave 1 has a displacement of 1.43 cm and wave 2 has displacement of negative 0.588 cm. To find the total or net displacement, the two were added together using the principle of superposition, which states that the total displacement at any point is the sum of the individual displacement of the waves at that point. So, y equals y1 plus y2 equals 1.43 minus 0.588 equals 0.84 cm. This means the particle's total displacement at position of x equals 6 cm and time equals 3 minutes is 0.84 cm. And that ends my discussion for today. Thank you everyone for listening. I hope you learned something new and enjoyed our topic. Have a great day!